Hello, welcome to another video. In this video, I'm going to look at daisy chaining as many of these as I can to see if the losses add up and we actually lose the signal after going through a whole bunch of these. So here's a little schematic. So we have a function generator, we have our transformers, we're just going to hook up a whole bunch of them, and then there's a 50 ohm load on the end, and we're measuring the voltage at the output and the voltage at the input. One of the things we're going to do is set our function gen so that the transformer it sees here is a 50 ohm load. So our voltage at this point and our voltage at this point should match. So we have to measure the inductance of our transformer. So I got this little thing here. It's kind of a cheap little tester. These are available on eBay and stuff, but they're pretty functional for basically no money. So I'm going to go ahead and turn it on and we'll let it run its test. I've already plugged in the leads, just one on one side and one on the other. So it looks like we got 1.05 millihenries and 0.5 ohms. Just going to push the test button one more time. So 1.05 millihenries. So I got a little formula set up here. So we have 1.05 millihenries, and that's our inductance. And there's a formula for reactance, which is XL equals 2 pi times the frequency times L. This would be in henries, this would be in hertz, and then this is ohms. So we're going to try for a 50 ohm load. So our formula is F equals XL divided by 2 pi times L over 1,000. That's to convert to the henries. So if we go ahead and we're going to plug in our numbers, we're going to have 50. So that gives us about 7,600 hertz. And since these probably have some variation in there, I'm just going to set for 8,000 hertz. Here I have a couple of SPICE models. The first one is a resistor model, and we can see the voltage drop across basically a string of resistors and one element of resistor, and how that changes the output voltage. So this is just a DC analysis. Here's a little bit of a more in-depth look at the SPICE analysis, where we actually are doing an AC analysis and looking at this as transformers. So each one of these sets of inductors is a transformer when you couple them in SPICE. And you can see I have a bunch of parameters defined in here, such as the inductance and the load resistor, the series resistance, and the coupling value for the actual transformers themselves. And then we're taking all kinds of measurements of some different parameters, and you can see that data presented here on the screen. Here's just a graphical representation of that data. I'll just leave this up for a few seconds and then I'm going to move on. If you want to take a look at this or get more information, just pause and read out some of the numbers. They're labeled along the top with V in, V out. All right, so what we got going on here is our function generator set to 8 kilohertz sine wave. That's going over, around, and into our first victim here. And then I'm tapping the voltage there and looking at it on this multimeter. This is also going to an oscilloscope, so we can look at the waveform coming from each of these. And then the output side comes over here, goes into a little 50 ohm resistor. Get this stuff out of the way here. The output of that's going into this little 50 ohm resistor right here, and that's feeding into this multimeter, which is looking at the voltage out and the frequency out. So you can see from one of these devices, it's pretty much flat. You know, the voltage here and voltage there are in very good alignment with each other. If we look at it on the scope, we see that the peak-to-peak values are actually both the same, and the RMS values are the same. They're within a few millivolts within the error of each other. So let's hook up a second one. All right, so now we can see we got quite a bit of attenuation. Looks like number one, the load is larger on the function generator, so we're getting less voltage on the input side, and we're also losing a little bit more to our output side. So we'll take a look at the scope image here. They look pretty close to each other. You can see that the orange line is a little bit smaller than the blue now, which means we are losing some voltage. Got some nice green and red for everybody. Here's the next one, and we can see again, now it's even lower. So we're losing quite a lot of voltage. Mostly the load is just getting worse and worse and worse as we put more of these on here. So the function generator can't push as much voltage down since it is a 50 ohm source impedance. So it looks like we're losing quite a lot on that initial number now. And the scope image is showing the same thing. The orange line is getting further from the blue line now. I think on the next one we're going to add 2 steps. Going to have to range down on our meter. May actually have to do that on here too. Look for millivolts now. Alright, so now we're even lower on both of our meters. And this is 6 in a row. And our oscilloscope is showing yet again. I'm going to have to actually range down the steps per division here. And we're showing even more degradation of signal. And we're also showing bigger separation between the blue and the red. And this is with 6, so we're looking for that bigger step. So it looks like I have 6 here, and I can get all the way up to 9. And then that'll be as many as I can get. And we're probably going to be down in the noise floor of these instruments at that point anyway. So, alright, so I think we're just going to go straight for broke and go all the way up to the max here. This will be the magic connection right here. And there it is. So 9 transformers in a row. And it looks like we're losing quite a lot of signal now. Going from the 90 millivolt down to 58 millivolt. And all the losses are from that initial, or from the actual transformers themselves. The losses are not actually from the load at the end of the line. We are feeding this with a 50 ohm source impedance though, so we're going to change this up a little bit. In this case, having this many different sets of coils in a line is going to basically load your 50 ohm source impedance down so much that you're just not going to be able to get any voltage through to the end. So here we're only seeing 58 millivolts at the output. Okay, so here's the next kind of iteration in this process. So I've gone ahead and added a low impedance amplifier. So now we can push more signal down this chain, and we can take a look at the losses at a little bit of a higher voltage. And what we see when we do this is we still get a fairly substantial voltage drop, but now we have a little bit more drive signal. We also see that when we look at it on the scope, you see there's a lot of spikes in the signal. That's actually the switching of the amplifier itself. So you can see there's actually a lot more noise on the signal, but in general the sign is still intact, and you can see that we still have about that same amount of drop across all of these transformers. So it's showing that the input impedance is actually not the reason for the loss. It's the chain is actually the reason for the loss. And so here we can see we still have that similar loss value, but now we have a little more drive voltage coming in. Next thing to try is getting some different frequencies through this thing and see how it works then. We'll be limited by that audio amplifier. Unfortunately, I don't have a higher frequency amplifier easily available. So let's try going down in frequency. Let's see, 7 kilohertz, 6 kilohertz. You can actually hear it buzzing a little there. 5 kilohertz, looks like it's getting worse. 4 kilohertz, worse. 3 kilohertz. Yeah, I'm not really seeing much improvement there. And let's go up. 10, 12, 13, 15. Oh, we're overloading our meter now. Go to AC there. So we actually got more voltage coming in. So this is telling you that's not very flat. But we can still see we still have a pretty substantial amount of attenuation through that signal. So now we're 15 kilohertz. Still got a pretty big drop across the devices, but yeah, not too bad. Still operating pretty good there. 20 kilohertz, still not bad. The load is actually smaller. Oh, we're overloading this one now. So the load is actually decreasing as we go up in frequency because the impedance of this is going to be higher. So this is putting less drain on this on its own. So each one of these in the series is putting a little bit less of a load. We're still seeing the losses though, because we're getting right now at 25 kilohertz, 0.85 here and 0.5 here. And the amplifier's doing just fine at that. We're at 500 millivolts per division now too, so quite a bit of change. I need to adjust my timing too, so you can get a little bit more close up on the signal. So now we're starting to see a little bit of phase shift in the signal as well as a voltage drop. Let's take it up. How far can we go? 36 kilohertz. Let's go to 40 kilohertz. Wow, sudden huge jump in the voltage. Having to go all the way up to 2 volts per division now. So this chain is working substantially better, but we're still losing a lot. And actually, if we look at this 4.1 down to 2.5, we're actually losing more at this frequency than we did at the lower frequency. And the scope image is showing pretty much the same thing. Much nicer looking sine wave now though, because the voltage has gone high enough that we don't actually see the noise superimposed on the signal anymore. I'm surprised that little amplifier is doing 40 kilohertz so well. Alright, how far can we go? Yep, and there it goes. So now we're losing signal. That's the, we've hit the limit of what this amplifier can produce for voltage. So 40 kilohertz is the limit of a sine wave for this power amplifier. Alright, so here's just a point in the middle, 37 kilohertz. Seems like we got a pretty good amount of transfer of voltage at this point. Alright, so here we have a table showing the results of the tests. What we can see here is we have our 1, 2, 4, 6, 9 transformers in a string, the real ones on the top, and the ratio there of 0.99 and the efficiency of 96 lines up really good with both our resistor model and with our SPICE simulation of the transformers in a string. And we can take a look at the 9 in a string and see that that also lines up. One thing to consider when you're looking at these is the coupling coefficient of the transformer. That was adjusted to get these relatively close. If you set that number too low, the efficiency values will tank. If you set that too high, it'll be optimistic about your efficiency. 1 is ideal. Any lower value than that is showing some real world loss in the core and the transfer between the two sides of the transformer. So if you don't need to have more transformers, don't have more transformers. Not that you would ever do this in the real world. Thanks for watching. Like and subscribe.